Hello everyone. Welcome to another session of notes. This is going to be notes 4.04, and this is word problems involving exponential equations. Okay. So today we're going to continue on our topic of exponential equations, and we're going to talk about today exponential growth and decay. And we're going to see some examples in that area. We're going to talk about how to identify if an equation is a growth or a decay equation, and how to solve some real-world problems that deal with these two types of equations or functions. Okay, so let me just read here. There are several situations in daily life that involve solving exponential equations. Most of these situations are classified as either an exponential growth or an exponential decay. If a real-life quantity increases by a fixed percent each year or other time period, then it is called exponential growth. The increase in the value of a house is an example of an exponential growth. We say that a house appreciates in value after every year that passes. So if you purchase a house, your investment should increase each year you keep that house. Continuing on here, we read, in a real-life quantity, if a real-life quantity decreases by a fixed percent each year or other time period, and what it means by other time period, that could be talking about days or months or years, right? Then it's called an exponential decay if we see a decrease, right? The depreciation of the value of a car is an example of exponential decay. So if you purchase a car and you drive it off the lot, it actually depreciates in value if it's a brand new car. And each year that you keep that car, it will decrease in value. Okay. And then at the bottom of this page, I have two formats or two equations that we'll see. Okay, so we have an exponential growth equation and an exponential decay equation. And I've kind of outlined here what the different variables of the equation represent and color-coded them, right? So if I'm wanting to know what's my final amount after I paid, let's say, initially I bought a house for a certain amount, and that house has an appreciation rate of R, and T represents time. It could be months, days, or years. Then we say that this is an exponential growth model. Okay. The other one on the right is an exponential decay. Same idea, same variables. What's the difference between growth and decay? Can anybody tell me? Does anyone notice the difference? Right? Yeah, growth has a plus and decay has a minus. Okay. And the last thing I want to talk about is how to identify whether an equation is an exponential growth or decay. We must look at the number that is the base of the function. So you notice we have a base in parentheses here, raised to a power of t. So this 1 plus r and this 1 minus r is our base. If that base is greater than 1, then we have an exponential growth situation. If the base is between 0 and 1, then we have a decay equation. And what are some values that you can think of that are between 0 and 1? What are some values that are between 0 and 1? And what should come to mind is either, fractions or decimals, right? 0.5, 0.25, 0.1. Any decimal is basically between 0 and 1, right? 0.99. Okay. So the next thing I want to look at is, let's look at some examples. Let's look at some scenarios where I have to identify if I'm working with a growth or a decay equation. Okay. So let me go ahead and slide over to the examples. Okay, so the instructions say, state whether the function represents an exponential growth or an exponential decay. Okay, and so in example 1, we want to look at the base. In this equation, we want to find the base. And remember, the base is anything that is raised to a power. You see how 3 over 8 is raised to the power of x? So we've identified, we've identified this base of 3 over 8. 3 over 8. And can anyone tell me, is 3 over 8 less than 1 or greater than 1? Let's see. 3 over 8 is equal to 0.375, and that is definitely in between 0 and 1. So it's between 0 and 1, so we have an exponential decay. We have an exponential decay because the base is between 0 and 1. Okay, example 2. What's the base here? Right, is it 3 or 10? And you should say, the base is 3 here. And 3 is greater than 1. So we have exponential growth. Exponential growth. Okay. The next one, the base is 4 over 3. 4 over 3 is approximately what? 1.333. And that is greater than 1. It's greater. It's greater than 1. So we have exponential growth. Exponential growth there. All right, and I think we're getting the hang of this, right? Here the base would be 0.5. 0.5 is between 0 and 1. So we have exponential what? Decay. Exponential decay there. And then one more. The base here is 1.2. 1.2 is greater than 1. So we have exponential growth. Okay, and again, these 5 examples just serve as a way to practice how to identify if we have an exponential decay equation or an exponential growth equation. Okay. Now, the next thing we're going to look at is we're going to look at 3 word problems, and we're going to see how to solve these. Okay. 3 word problems. This is number 6. It says the population of a small coastal resort town, currently the size of 3,400, grows at a rate of 3% per year. The growth can be expressed by the exponential equation the following, where P is the projected population, A is the current population, R is the rate of growth, and T is the time in years. Okay. And the question is, what is the town's projected population 5 years from now? Round to the nearest whole number. Okay. So we got to break this problem down and identify some key pieces of this problem. Okay. So first, let's identify what is the initial amount. In this case, A, the current population is 3,400, right? And as we keep reading, it says it grows at a rate of 3% per year. So 3% is my rate of growth. And we're interested in the question, it's in part A, it says, what is the town's projected population 5 years from now? So 5 years is T. So I'm interested in the value of P, the projected population. Okay? So let's substitute everything in. So I'm going to have P equals A, which is 3,400, parentheses 1 plus, how do you change 3% into a decimal? How do you change 3% into a decimal? It becomes 0.03. Okay, so I'm going to do 1 plus 0.03 raised to the power of 5. Okay, and so can we plug this into a calculator and get the results? Yeah, so let's do that. So we get P equals, if you plug it into a calculator, you get the following: 3,941.53. And remember, it said round to the nearest whole number. So we have 0.53, so that's definitely over 0.5, right? So I'm going to round up. So my final solution is the projected population would be approximately 3,942 people. In about 5 years, right, the population would grow to 3,942 people. Okay, let's look at part B now. Part B is asking, find the number of years it will take for the population to reach 10,000. Okay, keep in mind that the current population is how much? 3,400, right? So we want to know how many years will it take to grow to 10,000 people. And if we think about it, look at what we did in part A. In 5 years, it grew from 3,400 to 3,900. So think about that. Kind of think of a number of years that you might think that is. But what we're actually going to do is not try and guess, but actually solve. Okay. And what I want to identify here in this part, in part B, is what does the 10,000 represent in my equation? What does the 10,000 represent in my equation for part B now? It actually represents P. Okay? It represents P. So I'm going to plug in everything that I have. But let me write the equation one more time. This is the equation that we're working with, right? And I have P, I have A, which is 3400, I have R, which is 0.03, and the question is find the number of years. So I want to find T. So I'm going to plug in everything that I know, right? P is 10,000. A is the current population of 3,400. 1 plus R is 0.03 to the power of T. Okay, so I'm going to zoom in to part B now, so we can focus on that part. Now, how do I solve for T? How do I solve for T? Well, what's happening between 3,400 and this parentheses? There's some sort of operation happening, right? It's multiplication. So the opposite of multiplication is division. Could I also add 1.1 plus 0.03? Yeah, let's go ahead and do that first. So I'm going to copy 10,000, bring it down, copy the 3,400, and I'm going to rewrite this parentheses as 1.03 to the power of T. And then we're going to divide both sides by 3,400. Divide both sides by 3,400, so that 3,400 will cancel on the right. And if I divide 10,000 by 3,400 in your calculators, if you divide this, it's 50 over 17, I think. But as a decimal, let's see, 2.941. But let me keep it as a fraction. So it's going to be 50 over 17 equals 1.03 to the power of T. Okay. And now we have to ask ourselves, what do I do in this case? How do I get rid of the T? And what should come to mind is log. So we practiced on last lesson, I think it was 4.02. We're going to apply log to both sides. So we're going to have something like this. Log of 50 over 17 equals log of 1.03 to the power of T. And the log is going to allow us to move the T to the front. We're going to move the T to the front. So in my next step, I'm going to write log 50 over 17 equals T times log of 1.03. So all I did here is I took this T and I moved it to the front. And I need one more step to solve for T. I need to divide both sides by the log of 1.03 on the right and log 1.03 on the left. So we get cancellation on the right, and I get that T sorry. Let me fix this really quick. Zoom out here. t is equal to, not equal to, it's approximately 36.4970. Okay. And what I want you to do in your calculators is if you can type this out and tell me if you get the same value. We're going to type this fraction out. It's log divided by log, right? What's the base of the log if it's not given? Just kind of throwing it back there, right? It's base of 10. So you should get, once you plug it in your calculator, you should get 36.4970. And the problem says round to the nearest year. So this is about 49. So I'm going to round up from 36, I'm going to round up 1. So the approximate amount of time would be approximately 37 years. That's a long time, right? So it's going to take approximately 37 years for the population to grow to 10,000 when it started at a population of 3,400, right? If it's currently 3,400, it'll take 37 years to reach a population of 10,000. Okay? Two more problems, 7 and 8. Let's look at number 7. All right, number 7 says the formula, a equals p 1 plus r over 4 to the power of 4t, gives the value of an investment compounded 4 times a year, where p is the original amount of money invested, and r is the annual interest rate, and t is the time in years. Okay, and the problem says, suppose $100 is invested at 6% annual interest. What is the value of the investment after 10 years? Okay, so again, we're going to break down these values that we have given to us, right? And so what do you think 100 represents? $100 represents the original amount invested, right? So this is the p value. 6% represents the annual interest rate, so it's r. And lastly, what does the 10 years represent? That represents the time in years. So I'm going to plug in these 3 values into this formula here. Okay, so I'm going to get the following, right? A equals, what's p? 100. 1 plus, what's r? Again, remember, 6% as a decimal is 0.06. So I'm going to write 0.06 divided by 4, close parentheses. And some of you may be wondering, where did I get this 4 from, right? Remember, I'm just copying this formula given to us, and it's r divided by 4. 0.06 divided by 4. Then we're going to raise it to the power of 4 times 10. 4 times 10. Okay. So we can do some rewriting if we like. Some of you may like. Some of you may say, okay, I want to simplify some things, right? Can we put this parentheses together? What am I going to get when I add 1 plus this fraction? Well, if you type that parentheses in your calculators, you should get 1.015. And what is 4 times 10? It's 40, right? So simplifying a couple of things there. And now what we can do next is you can type all this in your calculator, and it should give you the value of the investment after 10 years. Okay. So what you should get, if you plug it into your calculators, you get a dollar amount of $181.40. Okay. So if you invest $100 in your bank, and your investment is compounded 4 times a year, and you wait 10 years, you should end up with $81.40 more than what you started with. Okay? All right. Let's look at part B. Let's look at part B. Okay. Part B says, suppose $250 is invested at 5% annual interest. In how many years will the investment be worth $500? Round to the nearest tenth of a year, to the 10th place. Now, part B, what I want to mention here is that part B is different than part A. Right off the bat, it's different because it's annual interest. Part A, if I zoom back out here, part A is also an annual interest rate, but it's compounded 4 times a year. This one on part B is compounded every year, annually. So I don't need to deal with the 4 that we have here. So what I'm going to mention in part B is we have a change of formula. Okay? So in part B, we're going to use the following formula. It's kind of similar to the one on part A, but it's a little bit different. Okay? So it's the following formula. 250 is P, 5% is R, and 500 is A. How much will how many years will the investment be worth $500? So twice what you made, right? Or, I mean, not twice what you made. When will the investment be worth twice your initial investment? Okay. So let's plug in everything that we have, right? A is 500. P is my initial investment of 250. 1 plus R. What I want to remind you guys again is, how do I change a percentage into a decimal? 5% becomes 0.05. So it's going to be 0.05 to the power of t. Okay. So one thing I can do, like I did on example 6, is I can combine what's in the parentheses. So it's just a simple step of writing this. Okay. Then I'm going to divide both sides by 250, kind of like example 6. We should notice that the 250s on the right will cancel. What's 500 divided by 250? It's 2 equals 1.05 to the power of t. Okay. Next, right, we're going to do similar to what we did to example 6. We're going to apply log on both sides. So log of 2 on the left and log of 1.05 t on the right. And when I use log on both sides, it allows me to bring the t to the front. So I'm going to end up with log of 2 equals t times log of 1.05. All right. And then I'm going to divide, because I want to solve for t, I want to divide both sides by log of 1.05, log of 1.05. This causes a cancellation of the logs on the right. And so t equals log of 2 divided by log of 1.05. Which will approximately give you, if you plug this in the calculator, will approximately give you 14.2066. And the problem said round to the nearest tenth of a year. So my final answer is going to be that t is approximately 14.2 years. Approximately 14.2 years. All right. Let's do one more. So let me slide over to the last problem in our notes. All right. This last one says, a doctor prescribes a dosage of 400 milligrams of medicine to treat an infection. Each hour following the initial dosage, the amount of medication in the body decreases by about 15%. This decay can be expressed by the exponential equation a of t equals a times 1 minus r to the power of t, where a of t is the amount of medication remaining in the body after t hours, whatever number of hours we're interested in, and r is the rate of decrease. Okay, notice here there's a minus because we're working with exponential decay, because the amount of medication that goes into your body decreases over time. Okay. And the question is, how much medicine is left in the body after 10 hours? So if you start with a dosage of 400 milligrams, what will this value decrease to after 10 hours? Okay. So let's identify some things, right? 10 represents t, the number of hours. 15% is r, the rate of decrease. And 400 milligrams, this is a. That's the initial amount. Okay, so let's plug in everything that we know. So we're going to say a, parentheses, what's t? Right, remember t is 10, close parentheses, equals, what's a? 400, right? 400 milligrams. Then we're going to do parentheses 1 minus 15% as a decimal is 0.15 to the power of, what's t again? That's 10, right? Okay, everybody with me so far? Now, what we can do again is subtract. If you want, we can subtract this parentheses here just to make it maybe a little bit less confusing. But so I'm going to copy everything and I'm going to rewrite the parentheses. And what's 1 minus 0.15? That's 0.85. Okay. Now, can we plug this into our calculator? Just what's 400 times 0.85 to the power of 10? And what you should get is 78.7497, which they want us to round to the nearest milligram. In other words, the nearest whole number. So 0.7, I'm going to round up to 79. Okay, so my final answer, 79 milligrams. Okay. So if my initial dosage is 400 milligrams, after 10 hours, my body will have, would have 79 milligrams left. Okay. Okay, let's finish it off with part B. Part B is asking, when would there be 60 milligrams of medicine left in the patient's body? So when it's asking for when, it's asking for a time. When will there be 60 milligrams of medicine left in the patient's body? And it says round to the nearest tenth of an hour. So this problem, part B, is interested in the amount of time. How long will it take for my body to have 60 milligrams of the medication left? Okay. So if I'm using this equation again, I'm just going to copy it. I'm interested in time. So this 60 milligrams is this value here. Okay. So plugging it in, I have 60. A is my initial amount, right? What was my initial dosage that I took? I took 400 milligrams of a medication, right? And then we're going to do parentheses 1 minus 0.15 to the power of t. And so again, we can copy everything and work out what's in parentheses, which would give me 0.85 to the power of t. Divide both sides by 400. (60 over 400). 60 divided by 400 will reduce to 3 over 20 equals 0.85 to the power of t. Okay, and then we're going to apply log on both sides. So we're going to have log of 3 over 20 equals log of 0.85 to the power of t. That allows me to, the log allows me to use the power rule and move the t to the front. And then I can divide log of 0.85 on both sides. Okay, which will cause this log and this log to cancel out on the right. And so if you plug this into your calculator here, it should give you a time that it's approximately 11.6732. Okay. Which, again, the problem said initially rounds to the nearest tenth of an hour. So I'm going to round from 0.6, I'm going to round up to 0.7 because 7 is bigger than 5. So that tells me to round the 6, to change the 6 up, move it up to a 7. So my final answer is it will take approximately 11.7 hours it will take approximately 11.7 hours until there are 60 milligrams left in my body. Okay, 60 milligrams of the medication. All right, thank you for joining me again. I hope these sessions have been helpful in explaining and kind of working out and working through the problems that we've had these past couple of weeks. And I hope you guys are continuing to stay safe and that you had an awesome Easter break. And have a great day.